what we are doing is a basic synopsis of alkyl halides and aryl halides. They can be prepared from alkanes. Alkanes, when you react in the light, you will get alkyl halide plus HX. This happens via free radical mechanism. From alkenes, we can add HX in a concentrated amount, or you can add HX vapors. Okay, that will cause alkyl halide to add up. But here, it will happen via Markovnikov's addition. Correct? You can see the
Yeah.
mechanism. The pi bond will attack on H plus. It makes a carbocation formation, which is a rate determining step. And that, when you react with X minus, will give you this product. Okay. If this is a product, that means it is following a Markovnikov addition. If this is a product P2, it is following anti-Markovnikov addition. The rate depends on the stability of carbocation. So intermediate 1 is more stable than intermediate 2. Product 1 is major than product 2.
Yeah.
Same thing with another question. You can see with HX, first carbocation will form. 1,2 hydride shift is taken. Once you get a positive charge, that's when X minus will attack. In this case, that X minus is chlorine. So Cl minus will attack, and that will make major product here. Okay. And if X minus attacks here, that will be minor product. And this is also minor product. Okay. Right.
Yeah.
The mechanism is more favorable. It is an electrophilic addition reaction, more favorable on a rate where carbocation get more stabilized. That means double bond should get more of alkyl groups. More alkyl groups means more stability of carbocation. So this is the rate of addition. Out of HI, HBr and HCl, HI will make a better addition here. Got it?
Okay.
Compared to that of HBr and compared to that of HCl. Next. Pi bond, when you react with X2 in the presence of CCl4, X and X will get added. And typically non-polar solvent like CCl4 or CS2 is more useful. The pi bond when attacks X2, it will go via formation of a bridge formation here like this, bridge halonium ion. And X minus will always attack on the more substituted side, breaking this bond. So this is the product you will get. So overall, I can say it is an anti-addition. Okay, it is an anti-addition, correct? So usually we know that if you take a cis molecule and make an anti-addition, the product you will get is 3O. Trans molecule, if you make an anti-addition, product you will get is erythro. Got it? Next, just like X2 addition, you can have BRCl, BRCN, ICl, NOCl, and HOCl. In all of them, whichever is more electronegative, that will add at the center, and which is less electronegative, it will act like an electrophile and add at the corner. Okay. So here Br plus will add, Cl minus will add here. Okay. Got the point?
Yeah.
Rx, when you react with NaI, I minus can attack here, X minus will leave, that will make it Ri. This is called Finkelstein reaction. Got it?
Okay.
The reaction is driven because of NaX precipitate formation. So NaCl and NaBr both will be precipitates in acetone. Any alkyl halide, if you react with AgF, COF2, HgF2 or SbF3, they all will convert into alkyl fluoride. And this reaction is called Schwarz reaction. Okay. Here, AgCl, AgBr, AgI will become precipitates. Any form of alcohols, I mean 1 degree alcohols, right? Maximum up to 2 degree alcohols, if they react with PCl5, PCl3, SOCl2 or SOCl2 in pyridine, all of them will give you alkyl halides. The first two drives via mechanism SN2, the second one drives via SNI, the last one drives via SN2 mechanism. This is the SN2 mechanism kind is known as Darzin's reaction. Got it? These five are very, very important reactions. I would want you to look over it properly Spend a minute of time and then we'll go. If you have an aldehyde plus PCl5, okay, basically the oxygen will leave away with phosphorus at P double bond O and leaves behind two chlorines to it. So that's why you'll get a geminal dihalides here. So geminal chloride here. Same way, RC double bond O R dash plus C PCl5, again two more chlorines here, correct? Acid plus PCl5, you will be replacing chlorine here now, okay? OH will be replaced with chlorine. Similar reaction here also, OR will be replaced with chlorine. If you have ether, both will turn into alkyl halides. Got it?
Mm.
Right. So this is a similar reaction happens with SOCl2 also. Got it? Mhm.
Yeah.
Next is Lucas test. This test is also a reaction for preparation of alkyl halides. Okay. So think this way. If you take 1 degree alcohol, react with concentrated HCl. But 1 degree alcohol अच्छे से react तो होगा नहीं because it cannot form a stable carbocation here. But see, concentrated HCl also does not break that easily. So to ensure that this bond breaks and H plus is available, what we should do? We should add anhydrous ZnCl2. On adding that, you will have available H plus ion. So then the lone pair will take H plus, becomes OH2, which is a good leaving group. Then carbocation can form, chloride can attack. But since it is 1 degree 1 degree position, carbocation is not formed. Directly Cl minus can attack. But this will take a lot of time since it is not forming a carbocation, and attack on that primary position will be difficult. That's why for 1 degree, the attack will take a longer time. Second, if it is 2 degree, it will take 5 to 10 minutes. Reaction would happen via SN1. Okay. And lastly, 3 degree. 3 degree happens much faster. Immediately there will be turbidity. The minute alkyl halide will form, it will appear like a turbid. Correct? Got it? So like buttermilk. Understood? So white color turbid will start forming. The minute you have a turbid, that means it is understood that there is uh, a tertiary alkyl halide forming.
Yeah.
Okay, beta? Right.
Yes.
Now, whenever it comes to alkyl halides, the substitution reactions are something which we need to check. And in substitution, you start with SN2, then SN1, SNI. Those are all the cases. Check out. SN2 is a one-step reaction. There are no intermediates, no carbocation, no rearrangement. So like a nucleophile OH minus can attack here, Cl minus can be relieved, and you'll get methanol and NaCl. The OH minus has
Mm.
to attack from the back side, Cl have to remove from the front end. The intermediate which forms is trigonal bipyramidal. So stability of this intermediate decides the rate of reaction. Okay. So if you want to decide the stability of this stability of the product, then this transition state should be more stable. Clear it up. So if
Mm.
this transition state has to be more stable, that means you can see these three hydrogens which you can notice, right? These three hydrogens, if you have anything bulkier here instead of hydrogens, correct, then the reaction will become slower. That's why rate of SN2 depends upon the hindrance bond on the CX. Got it? So more is the hindrance,
Mm.
less is the rate of SN2. So that's why you will see one halide will be the most reactive, then ethyl, then isopropyl, then tert-butyl. Okay.
Mm.
Overall rate of the reaction, if you notice for SN2, this is the order that you need to remember. Very important order. Okay. So this is something I would request you to write and practice once, beta. Rate of SN2 also depends upon which type of alkyl halide we are taking. Ri is greater than RBr, RCl, and RF. Now, the strong nucleophiles always favor SN2. What are all the strong nucleophiles? OH minus, RO minus, N3 minus, I minus. This C triple bond C minus, pH S minus. NH3, PHO minus. These are all strong and favorable nucleophiles.
Hmm.
Got it? Rate of the reaction depends upon both substrate and nucleophile. Molecularity is 2, order is 2. Okay. Now, in case if there is a chiral center, configuration can be inverted, and this inversion is called Walden's inversion. So you can see 1, 2, 3, 4. This is the way it is present here. So 1, 2, 3. That means it is an R configured because it is going clockwise. When N3 minus attacks, it will attack from the back end, remove iodine. So now, if you notice the clock here, so we'll be starting with 1 here, 2 here, and 3 here. So this has become anti-clockwise, so it is becoming S. So the absolute configuration R will become S if chiral center is present when SN2 mechanism is happening. The solvent which favor SN2 are polar aprotic solvent like DMSO, DMF, ethers. These are favorite or favorable solvents for SN2. Any doubt?
No, sir.
Next. Any general substitution you can see when nucleophile substitutes you get R, Nu and X minus. The X minus which is leaving is called the leaving group. Okay. Now leaving group ability depends upon its basic strength. Stronger the base, weaker the leaving group and vice versa. Correct. So basic nature of the halides, if you notice, F minus is more than Cl minus, Br minus and I minus. But when it comes to leaving group, I minus is better leaving group than Br minus, Cl minus and F minus. Okay.
Hmm.
Just a second. Next is this one. CH3 minus from left to right. CH3 minus is a better base than NH2 minus, OH minus and F minus. So this is basic group. So leaving group ability will be exactly opposite. Got it?
Hmm.
And overall, if you notice this leaving group, it is based upon their pKa values. So water would have higher pKa value. That means it is a weaker acid. So OH minus is a stronger base. HI is the a very strong acid. So I minus is a weaker base. Hence, it is a better leaving group.
Hmm.
Okay, beta.
Yeah.
So notice if this is 1 and 2 case, both of them are reacting in the presence of CH3O minus. Correct. So CH3O minus can attack here, it can attack here. Where is the rate more? Obviously, I minus is a better leaving group, so I2 is greater than 1. Got it? Next. N2 and CO are excellent leaving groups. So that means if they are directly connected to any alkyl halide like N2 plus or CO plus, they can leave very, very easily. Got it? Apart of this OTF, that means CF3SO3 minus, known as triflate, ONS, which is nosylate, OBS brosylate, OTS tosylate. This is the order of the leaving group, and all of them are excellent leaving groups. Got it?
Hmm.
See, strength of a nucleophile is called its nucleophilicity. So whether it will make it as a better nucleophile or not, that depends upon its strength. Now notice, if a base will try to go and extract H plus, it does not require any direction. It can attract from any direction and it can still get the H plus away. But if it is acting like a nucleophile, then nucleophile can only make an attack exactly from one direction. So
Hmm.
orientation becomes very, very important here. Okay. Hence,
Yeah.
bulkier the nucleophile, difficult it will act like a good nucleophile. Correct. So nucleophilic
Yes.
strength, if you notice, this is less bulkier than this one, and this one. So you can see bulkiness is increasing. So nucleophilic strength is decreasing. Second thing, nucleophile will be, in parallel to basic nature, right? As long as these cases are concerned, pK value cases are concerned. But the connecting atom should be same. That is, all of them are connecting from oxygen end. But this one is a stronger base than this one, than this one. This is has the weakest base form. Got it? And nucleophile is also proportional to basic strength if you go from left to right in the periodic table. That is CH3 minus till F minus. Both nucleophile and basic nature will have same thing. SiH3 will have same as pH2 minus, SH minus and Cl minus. That is from the next period, elements.
Oh.
Next, nucleophile directly proportional to basic nature of the group. So that is in non-polar solvent or polar aprotic solvent or in gaseous state. So these are all the non-polar solvents. These are all polar aprotic solvent. So in these solvents, fluorine will be stronger base and stronger nucleophile, and OH minus will be stronger base and stronger nucleophile. Okay. But if
Mm.
you're talking about polar protic solvent like water, ammonia, alcohol, acid, in that case, nucleophilicity will completely be opposite. I minus will be stronger nucleophile, then Br minus, Cl minus, and F minus. The
Oh,
same goes with group 16, same goes with group 15. So this is the sequence of nucleophilic nature. Correct? So
yeah.
go through it quickly once. Please try to get to the idea what exactly is the nucleophilicity, how does it vary. These are the cases where SN2 reaction is not observed. For example, if I have vinyl chloride will have a double bond character due to the lone pair of chlorine, because of which a nucleophile does not attack and cannot replace the chlorine. Got it? Second, the same logic applies to phenyl also. The lone pair will always be in resonance with the benzene, so no attack. Third, if you have a
Mm.
bridge position, the sigma star which is inside, that cannot be attacked from the backside with nucleophile, hence there is no SN2. 3-degree alkyl halide is very difficult to make a nucleophile to attack from the backside because of the bulkiness. And here
Mm.
in a 3-membered ring also, you will have a sigma star orbital hiding within this ring, so it is difficult for nucleophile to attack. So remember,
Mm.
these are those 5 cases where SN2 reaction is not possible. Clear?
Yeah.
Next. Coming to SN1, SN1 is, one-step reaction here. Sorry, two-step reaction here, where you have a first carbocation formation. So you can see step 1, a carbocation is formed. And carbocation may get rearranged if there is a possibility. Then nucleophile will attack, and thereafter maybe deprotonation, everything will happen, and finally forms a product. Okay. Rate is directly proportional to substrate, and nucleophilic strength is not the objective here. So order of the reaction is 1, molecularity is 1. So rate mainly depends upon the stability of carbocation. Now this is the order of SN1 that you need to remember, in which case what is the order, okay? SN2, I'm sure you have written it right, SN2.
Yeah.
Same way write it for SN. Check out. It is favorable in polar protic solvent. SN1 is favorable in polar protic solvent. Next. If solvent is nucleophile, then the reaction is called solvolysis. Got it?
Yes.
Clear? Hmm. And which are the cases where SN1 is not observed? Check out. These are the cases. Clear? Same vinyl chloride, correct?
Mm.
Same vinyl chloride, nucleophile when you have the lone pair is resonance stabilized, so carbocation बन नहीं सकता है. Same with phenyl chloride. Same, carbocation cannot form at the bridge position, and here it cannot form carbocation because it is an anti-aromatic ring. And lastly, on 3-degree, I mean the cyclopropyl group also, carbocation is extremely unstable, so यहाँ पर भी नहीं होगा. Correct? So these
Yeah.
are the cases, 5 cases of SN1 where reaction cannot happen. Okay. Mm.
No answer. Yeah.
And see the examples. So if you have 1, 2, 3, 4 examples, please check out in which case SN1 and which case SN2 is favorable quickly. Okay. If you have a problem, let me know. 1, 2, 3, 4, 5, 6. Check out all these 6 ones. Okay. And notice which
Yeah.
case is going SN1 and which case is going SN2. If it come to this 1 degree, although it looks like SN2 hona chahiye because being 1 degree, it is extremely bulky on the left hand side. So therefore it will favor SN1. So first it will form a carbocation, methyl shift will take place. Okay. And
Yeah.
carbocation will shift here, OH minus will then attack. Correct.
Mm.
Even if you have this kind of 1 degree alkyl halide, chlorine can leave, carbocation can form, bond can break, ring expansion can take place, and OH minus can attack. So although they are 1 degree, in these cases they will favor more of SN1. Correct?
Yes.
Next, if by chance I have a benzyl group here and uh, G group is present, and imagine these are all the groups that can be present on that group, okay,
Hmm.
on benzene. If it is SN1, you are checking stable carbocation, है ना? So therefore,
Hmm.
anything which is donating like NH2, OH, OCH3 methyl, these are all donating, electron donating group. So they will stabilize it. Chlorine on NO2 are withdrawing. But when it comes to SN2, direct attack will take place. So delta positive should be high, which means group should be withdrawing. So which are more withdrawing now? Exactly opposite. So NO2 is
Hmm.
more than Cl, H, methyl, and so on, right? So SN1
Ah.
and SN2 will go at exactly opposite when it comes to benzyl chlorides. Clear?
Yeah.
Notice what is SNI reaction. SOCl2 attack on alcohol here. So lone pair will attack, Cl minus will go. This will come, Cl minus will take H plus, HCl will go. Just now I told you this mechanism already. Okay. So we have
Yeah.
RO, S double bond O Cl. Now here, if there is no pyridine, right? If there is no pyridine, this chloride will directly attack here, internally and make it as RCl and SO2. So that internal attack is what we call it as SNI mechanism. Okay. So in
Yeah.
SNI mechanism, the reaction is undergoing a retention here. So for example, if this is S configured, with PCl5 it will become R configured. But with SOCl2, it will become S will remain S configured. So where the group is going, at the same position, chlorine will be attached. Done?
Hmm.
Now you can see that if a question is given like this, and these are all the options given, what are the correct structures? So you can see OH is here, Cl is on the same, orientation. That means it is wrong because it is SN2, it should get reversed. So this is correct. Acha, this if you put a mirror like this here and see, this is how it appears, isn't it?
Yeah.
So whatever that was going inside will come outside. So this structure and this structure is same. And again, this is wrong, and because these two are same. Okay. While when it comes to SOCl2, now this one and last one, these are correct because they are retention form. These two are inversion forms. Done.
Yeah.
Next is SNNGP. SNNGP is called unchimeric effect. Here, normally what you notice it when you react with water, attack here, Cl minus is relieved, carbocation will form and then rate will come as R1. But the same reaction when there is a sulfur in between here, right? Then the reaction will
Yeah.
be almost 600 times of R1. Okay. What happened here is the lone pair on sulfur has actually helped internally to remove this chlorine. So on removing, we will get a positive charge on the sulfur here now. And then water will attack on this position. Bond will break here. So this is how you will get it.
Hmm.
Clear?
Hmm.
So you will see inversion plus inversion will give you a retention form here. Okay.
Okay.
So
Oh
that's
yeah.
how it will undergo a retention form.
Hmm.
Clear? Right. Now,
Yes.
next. Now you can notice it from here. Sulfur attacks here. Chlorine will relieve. You will get a ring structure here. Now water can attack from both the ends here. Both the ends are open commonly. So you'll get 50% of this, 50% of this one. So overall, you will get an enantiomeric mixture or racemic mixture in both the cases. Okay.
Yeah.
Notice same way here. OC double bond of CH3 cannot help this chlorine because they are on the same direction. Okay. So normal SN2 mechanism is favorable. But if they are on the opposite direction, from the backside oxygen can attack, remove chlorine, make a ring structure. And then after again water attacks, the retention can take place. Okay. And because
Yeah.
oxygen, when it is attached here, the same water molecule could have attacked here or here. So two
Hmm.
products will come. That will be racemic mixture of both of them. Done?
Yeah.
Same way, if you have an OTS group here and there are two different carbons. Imagine this is carbon 12, carbon 14, and benzene is connected to it. So as OTS goes, the lone pair on benzene will attach, and this is the intermediate you will get. And that's where methanol can attack, bond can break here, or methanol can attack here, bond can break here. Okay, both will get 50-50 percentage.
Hmm.
Read out
1 second.
SN right? Stereochemistry of SN1 is what you know. See, when it comes to SN1, polar protic solvent is used, correct? So this way, water molecule, for example, is polar protic. So that will help help in breaking the bond of alkyl halide. Okay. So that's how you will notice that carbocation and chlorine which is present, right? Now, water will be able to separate this part and this part. While doing this process, what happens, water always try to keep attacking, but chlorine is present, so it is not allowing water to come in between. But as you start opening up, as the bond starts breaking, water will already start attacking from the backside. That means thoda sa inversion already start ho jayega. A small percentage of inversion already starts. And this
Hmm.
begins in a case where it is a tight ion pair. That means alkyl halide and chloride, alkyl and chloride are tightly attached to each other. Okay.
Hmm.
And thereafter, water will attack from either of the ends, and you will get rest of the 95% undergoing racemization. That's why you will
Okay.
notice if a, a compound is R configured with pure form, adding water, you may not get exactly 50% and 50% inversion and retention. You might get 52% of inversion and 48% of retention. So
Hmm.
percentage racemization is 96%. Okay. Now why this has happened? This has happened because due to tight ion pair, 1 to 4% or 1 to 5% will be undergoing inversion before it can start racemization. Okay.
Hmm.
So if carbocation stability increases, racemization percentage increases and inversion percentage decreases. Now notice if the water quantity is decreased and acetone quantity is increased, racemization will increase. So
Hmm.
100% water, 95% racemization. 50% water, 50% ethanol, 97% racemization. If 20% water, 80% ethanol, acetone, 99.9% racemization will take place. Got it? Now, check out carefully. If you have SN1 and E1, right, which one should we go for? In which case, what we should go for, right? Whether we should go for SN2, whether we should go for SN1, and so on. So, first, let us see SN2 versus E2. If you have CH3Cl, there is no chance it can go for elimination because there is no there is no beta carbon, correct? Beta carbon ke bina we cannot have any elimination. Okay. So now notice in all these cases, if you have a strong nucleophile, they'll always favor SN2. So notice in all the cases, SN2 reaction is favorable. देख लो बेटा ध्यान से.
Hmm.
It is only favoring SN2.
Yeah.
Right. Next, if you have an ethyl chloride, now there is a chance of E2 happening, but the base should be very, very strong. Correct? Clear, beta? So notice in these two
Yeah.
cases, the base is very strong. Okay, tert butoxide or NH2 minus. In such case, E2 is more favorable.
Hmm.
Clear?
Yes.
Next, please do check these two cases. I hope you did understand this part. Shall we go ahead?
1 second.
Hmm. So in this case, it is being secondary. Okay, being secondary, you need to judge whether it will go for SN1 or SN2 depending upon strong or weak nucleophile. So weaker nucleophiles go for SN1, stronger nucleophiles will go for SN2.
Into.
But if the base is very strong or heat is given, definitely it will go for E2. Okay. So analyze them carefully. Now let's notice the tertiary case now. Okay. In case if you have a tertiary alkyl halide, right, what is the reaction that will happen? Have you noticed in no case there is SN2? So either it is SN1, SN1, E1 or E2.
Hmm.
Right? So it could be either SN1, E1 or E2. E2 normally favorable at a strong base. Okay.
Yeah.
SN1 and E1 both are favorable at weak base. But SN1 और E1 में सिर्फ एक ही difference है heat. Only when the heat
Huh.
is given it is E1. Otherwise it is
Okay.
SN1. Got it?
Okay.
Please check.
It is an STP.
Notice. The reaction like Williamson synthesis, ammonolysis, Stephens reduction, and polyhalogens, these are the next thing that you need to learn. Check out. Starting with Williamson ether synthesis. RO minus, when you react with RX, O minus can attack R, X minus can leave via SN2 mechanism. This is called Williamson ether synthesis. To generate RO minus, you take alcohol in the presence of sodium, you will get alkoxide. Got it?
Yeah.
And alkyl halide which is getting reacted must be SN2 ready. That means it can be 1 degree, maximum 2 degree, allyl or benzyl. You cannot have other groups. Correct? If there are other
Hmm.
groups, that means it might go for elimination and so.
Yeah.
So you can see CH3O minus can attack, X minus can leave. So you will get this product.
Yeah.
Third butoxide can attack, X minus can leave, SN2 can happen. But if you have this as tertiary butyl chloride, then elimination can only happen. So E2 will be favorable in that case. Okay.
Okay.
Phenoxide, when it attacks, it is simple SN2. And here this attack is not possible because it is at benzyl phenyl position. So phenyl group with X will have and double bond character by which there is no reaction. This is
Yeah.
benzyl. Benzyl will definitely give you SN2 mechanism. And
Hmm.
again, this is phenoxide will not give any reaction here. Phenoxide will not give any reaction at a bridge position also. So these are the cases which can never be possible to prepare by Williamson ether synthesis. You cannot prepare via Williamson ether synthesis. Can you see the cases?
Yes, sir.
Right. Now, phenol attacking on methyl, removing oxygen. This is also like a Williamson synthesis, but in acidic medium. But in slightly basic medium. So OH minus basically takes away H plus. O minus will attack. This bond will break. Same way, phenol. When you react with uh, alkyl halide here, the lone pair can attack. Cl can leave, and you will get the same product.
Yeah.
Ammonolysis. Lone pair from nitrogen can attack, remove chlorine. This is an SN2 mechanism. But the problem here
Hmm.
is Cl minus will take H plus, convert into 1 degree amine. Now 1 degree amine can again act like a nucleophile. That itself will attack on the alkyl halide. You will get 2 degree. 2 degree can attack 3 degree. 3 degree can attack 4 degree. So that means the reaction will only stop once the 4 degree amine is been formed or 4 degree ammonium salt is formed. Okay.
Okay.
And if I take alkyl halide in excess, then 4 degree is major. But if I take ammonia in excess, then 1 degree is major.
Okay. Yes.
Stephens reduction. When you have cyanide here and react with SnCl2 and concentrated HCl, it will give you aldehyde.
Yeah.
So basically, tin chloride with HCl will form SnCl4 and cyanide will undergo reduction to form imines. And then SnCl2 plus 4HCl will give you this part, releasing two nascent hydrogens. So, and you know that imines on hydrolysis will break this bond and convert into aldehyde. Okay.
Hmm.
So for aldehyde preparation, this is best used. Got it?
Yeah.
And to give you a quick idea, cyanides when you react with H2, lithium aluminum hydride, sodium ethanol, rann nickel, and zinc, it will all form 1 degree amine. Okay. But if you hydrolyze the cyanide form, it will convert into acids. Got it? Hydrolysis of
Yeah.
cyanides will give you acids both in acidic medium as well as basic medium. Okay. But reduction will give you amines.
Yeah.
See this reaction. When you react with KCN, Cn minus will attack, Cl minus will go. You'll get cyanide here. Hydrolysis, acid will form. Soda lime decarboxylation of acid will make you hydrogen here, correct? This is carbon
Hmm.
dioxide will go away. So you'll get butane. But if you react with H2 and nickel, cyanide will get reduced. You will get, amine here. Clear? And CH3Cl, when you
Yeah.
react, lone pair will again attack here. You will get 2-degree amine.
Hmm.
Done. Next, check out polyhalogens. If you have two chlorines, we call it as geminal dihalides, on the same carbon. If they are adjacent
Hmm.
carbons, vicinal dihalides. Okay. Geminal dihalides reaction on hydrolysis, both will go. 2OH will convert into aldehyde. Aqueous OH
Hmm.
minus, same thing.
Yeah.
Ag on heating means you will get, carbene here and take 2 moles of carbene. You will convert that into a double bond.
Yeah. Okay.
Zinc with HCl, chlorine will be removed, hydrogen will come. With KCN, two cyanides will come. On hydrolysis, COH will form. And if you have beta diacids here, this is beta diacids. Beta diacids on heating, one of the acid will convert into CO2 and rest will be present as acid. Okay. This is the product formation. Okay. So you can see
Okay.
malonic acid on heating will give you acetic acid plus CO2.
So can
Correct.
you explain the last step? Beta acids का.
बीटा डाइएसिड इज सेम एज दिस वन बेटा मैलोनिक एसिड को हीट करोगे तो क्या आएगा ओके
सर उसमें
ऐसा
एक कार्बन कम हो रहा है.
हाँ बेटा कम हो जाना चाहिए ना डीकार्बोक्सिलेशन हुआ है
हाँ हाँ
अच्छा
हाँ
लास्ट
यस
में
यस.
कह रहे हो इधर
हाँ.
हाँ 1 1 2 3 4 ओके यहाँ पर एक कार्बन रहेगा
हाँ ओके. यस.
ओके
हाँ.
नेक्स्ट बीटा कीटो एसिड में भी हीट करोगे तो CO2 चला जाएगा यू विल गेट कीटो
हम्म.
नेक्स्ट इफ यू हैव geminal dihalides with alcoholic KOH one one Cl and one H will go away फर्दर एलिमिनेशन के लिए NaNH2 ही चाहिए होगा alcoholic KOH cannot do so with NaNH2 you will get this further elimination NaNH2 excess will give you this one
या.
got it vicinal in aqueous NaOH you will get OH and OH hydrolysis will give you OH and OH. Cyanide will give you two cyanides. On heating, you will get, first on hydrolysis, you'll get acid. On heating, you'll get, this is succinic acid. So that on heating will give you anhydride. With
हम्म.
NaI, you will get two iodines. And two iodines on vicinal position is unstable. That will go away and you will get alkene. Okay.
हम्म.
Uh, so quickly check out vicinal cases. Any doubt? Clear?
या.
Will we go ahead?
हम्म. यस सर.
Right. Okay. So whatever we have discussed so far, then we can start solving. Okay. In polyhalogen, haloform reaction is something which you need to learn. Haloform reaction. Okay.
या.
Haloform reaction is when you have an halogen here, like Cl, and then you are treating this with, you know, something like I2 in the presence of NaOH. Got it?
या.
So in the presence of NaOH, first you will get an OH group. Correct? So let me do step by step here. So alkyl halide, when it will react with NaOH, it will first become alcohol, 2-degree alcohol here. Okay. And step 2, this alcohol in the presence of OH minus will become alkoxide like this. Okay.
या.
Step 3 is that this alkoxide, when you treat with I2,
हम्म.
it will convert into O and I plus I minus. Okay. Step 4, O and I here, correct? And then OH minus, the hydrogen which is present here, it can take this H plus, bond will shift, I minus will come. So again, you will get this into keto form plus H2O plus I minus. Okay. Now step
Yes.
5, you are basically trying to react with ketone. Ketone, when you react with I2, okay, of 3 moles in the presence of base,
Yes, sir.
then you will get this carbon has Ci3. All of that will replace, all of those hydrogens will replace with hydrogen, with iodide.
Yeah.
So once you get this double bond O Ci3, and this when you treat with OH minus, it will attack. You'll get this as OH plus Ci3 minus. Ci3 minus will take H plus from here, and you'll get double bond O minus plus CHI3. So what did we get? Halo form.
Hmm.
So with chlorine, bromine, iodine, both, for all of them it is same. Okay, reaction rate.
Yeah.
If you have alkyl halide, sorry, reaction rate depends upon uh, whether you are taking iodine, bromine, or chlorine. It does not matter. The reaction rate is almost the same.
Yeah.
Clear? So yes, beta, this is about the haloform reaction that you need to know.
Yeah.
Okay, please check. In the case of haloarenes, what we need to learn, got it? First, the preparation. Here, haloarenes means you will have benzene with a halogen on it.
Hmm.
These are called haloarenes. So if you notice the preparation, out of many reactions on benzene, if you react that with any X2 in the presence of iron, or X2 in the presence of AlCl3, or X2 in the presence of FeCl3, like this, or FeX3, they
Hmm.
all will give you only one product, that is halo alkane, halo benzene. Got it?
Yeah.
This is what you will get. Okay. Next. And whenever it comes to other reactions that include aniline, NH2, right? So this is the first set. Second one, aniline, when you treat with HNO2, it will turn out to be N2 plus, which is diazonium chloride salt. And diazonium chloride salts have lots of reactions here. Got it? Starting with hydrolysis, H2O, heat or warm water, that will convert into OH. Now this type of a reaction is called as ARSN1. So it is happening via SN1. That means carbocation ban raha hai. Then the water will attack. So it is ARSN1. It is aryl carbocation which is forming. Got it? So next, if at all we have reaction with halogen like CuX here, correct? CuX here. In case if at all I'm treating that with CuX, now X could be chlorine, bromine, or cyanide. Then you will get this as X here, and this will happen via ARSN. Sorry, this will happen via radical mechanism. So this is called SET mechanism, single electron transfer mechanism. Got it?
Hmm.
Next, same way, if it happens via other reactions are, if I take HF with BF3, So first it will become some kind of a salt here, like N2 plus and BF4 minus. And this on heating will give us, F minus and BF3 and N2. Now this reaction is same as the earlier, which is ARSN1 kind. This will happen via ARSN1 kind. Correct?
Yeah.
Now this reaction is called Sandmeyer reaction. Sandmeyer reaction. And this is called Boltzmann reaction. The next reaction here is reacting with X2 directly, X2 in the presence of copper dust. This gives the same type of reaction as that of X here. This is also a single electron transfer mechanism, and this is called Gattermann reaction.
Yeah.
So this will be called as Gattermann reaction. Okay.
Hmm.
So these are some reactions that you need to remember. Correct. The third way of preparing aryl halides is when you take, uh, what is the other way? No. Benzene directly, if at all we react with Cl2 in the presence of H nu. So you can get Cl. Okay. But it should be one
Hmm.
equivalent. But if you are taking excess of it, Cl2 excess, and then H nu, then addition will favor. Now this time addition will favor. So you will get all chlorines on this place. So you'll get C6, H6, Cl6. This is called gamaxene.
Hmm.
So just remember in what case what will happen. Okay.
Yeah.
What are the chemical reactions here? Chemical reactions wise, when it comes to aryl halides, you will notice that first, if you have a halobenzene here, correct? So
Yeah.
that when you react with NaOH fused NaOH, so then you will get this as O minus Na plus. Okay.
Hmm.
That on hydrolysis will give us phenol. Correct. Now this is called Dow's process.
Hmm.
Okay. Mechanism in
Yes.
this case will be via, benzyne form. Benzyne banega isme. Correct. Usually the temperature term is important here. Temperature would be around 623 kelvins. Pressure is around 300 atm. Clear? So this is the reaction that will take place. Okay.
Yeah.
Right. Next, the rate of reaction would be much better in case if you have any withdrawing group here. So that means if you have anything like NO2 here, then OH minus will attack fused form. Now this will form as OH here and NO2, but this time the mechanism is ARSN2. ARSN2 is the case where first the addition of OH minus will take place. Okay. And this will
Yeah.
start moving around and make it a resonance hybrid like this. Negative charge with X and OH minus. Okay. Now this is what we call it as Meson-Heimer complex. Correct. And thereafter X minus will leave and retain back the OH here. Correct. So here if the NO2 presence will help the stability. Correct. Stability of this
Yeah.
complex. So that's why more the NO2, more is the rate of reaction. So if you notice the rate of ArSN2 will be halogen with one NO2 here less than halide halogen with two NO2 groups here, and that is less than NO2 with 3 NO2 groups here. Right. This will be the order of AR-SN2. Done.
Hmm.
Right. Within the halogens, if you compare, correct. So rate of AR-SN2, if you are comparing for halogens, then in the case of halogens, fluorine is greater than chlorine, bromine, and iodine, because fluorine can stabilize the negative charge much better. So that's why fluorides will be making a better reaction here.
Hmm.
Got it? The typical reactions that you need to understand from here are these. Suppose if you have, let's say, chlorobenzene with NO2 here, and you are reacting that with NH2 and NH2 hydrazine. If you are directly reacting with ammonia, if you are reacting with OH minus,
Hmm.
if you are reacting with pH S minus, if you are reacting with cyanide CN minus. Okay, what are all the products you can get? Let me take one more case here, RO minus. Okay, so in all these cases, what do I get? I will get here as NH2 with NO2, and here I will get NH2, this is NH3, sorry, and here you get NO2,
Yeah.
and here I will get this as NH2, sorry, OR, and here we will get NO2. Now here
Yeah.
OH can be replacing that easily, while pH S minus we will have S and pH here with NO2, and lastly cyanide will also give you this reaction. Done. These
Hmm.
are all the AR-SN2 reactions. Okay. If at all it is being given like this, chlorine with a methyl group, only chlorine,
Hmm.
chlorine with NO2 at meta position, chlorine with another chlorine here. Got it?
Hmm.
Now in such cases, if at all you are reacting with NaOH here, correct? No
Yeah.
reaction takes place. Then no reaction in this case. Okay, because we require NO2 should be present at the para position only. Minimum one NO2 should be present, and that too at para or ortho position. It cannot be at meta position.
Yeah.
Right, but next, if by chance if there is a fluorine here, okay, and you have NO2 at this position, NO2 at this position, and CH2Cl here, and this,
Hmm.
if at all I am reacting that with pH S minus first, the first reaction is always will be alkyl. Alkyls are more reactive form. So one equivalent will give you this NO2, NO2, and F. But if I give you two equivalents, pH S minus of two equivalents, at that time both will get replaced. So that means here SPH will form, Na2 will be here, NO2 will be here, and here we'll get this as pH S minus.
Hmm.
pH S minus got attached. Okay. This
Yeah.
is the product if you have two equivalents. Done.
Yeah.
um, Next, what do we need to learn out of this? Let me remember if I'm forgetting anything.